All right, let's get right into it. We all know the planet's getting warmer. That's not the mystery. The real head-scratcher is this. Why is it so incredibly hard for scientists to tell us exactly how hot it's going to get? I mean, we have supercomputers, we have mountains of data, so what's the holdup?
Well, believe it or not, the entire puzzle really boils down to this one number. Just 1%. That's it. For the last 200 years, all of our human activity combined has only disturbed the Earth's massive energy budget by about 1%. A tiny, tiny nudge in the grand scheme of things.
But, as you can see here, a tiny nudge can have gigantic consequences. That 1% push corresponds to this absolutely dramatic spike in greenhouse gases. We're talking about going from a stable 278 parts per million of CO2 in the air to over 400. We've fundamentally re-engineered our atmosphere. Now, to understand how that actually changes the temperature, we need our first major clue. It's a concept called radiative forcing. It sounds technical, but just think of it as turning up the thermostat on the planet. It's a measure of how much extra energy, how much extra heat we're trapping.
And when you look at the evidence, the main culprits are pretty obvious. We know with a lot of confidence how much gases like CO2 and methane are cranking that thermostat up. They're trapping heat, they're pushing the system towards warming, and we've got a really good handle on those numbers.
So you'd think, case closed, right? More gas, more warming, predictable future. But it's not that simple. Here's the twist in our whole scientific detective story. The math doesn't quite add up, which means something else has to be in the mix. What if something has been pushing the thermostat in the other direction?
And here it is, the wild card, aerosols. These are tiny particles from industrial pollution, think smog, sulfates, that kind of stuff. And they actually create a cooling effect by reflecting sunlight back into space. But just look at the uncertainty on that number. It's huge. This one factor is the single biggest unknown in the entire climate puzzle.
Okay, so you have this tug-of-war in the atmosphere. On one side, you have greenhouse gases. They're in it for the long haul, sticking around for decades, even centuries, constantly warming things up. And on the other side, you have aerosols. They're gone in a flash. They wash out of the air in about 10 days. This difference is absolutely critical.
Before we see why, we need our second big clue, climate sensitivity. So if radiative forcing is the push on the climate, climate sensitivity is how touchy the system is. How much does the temperature dial actually move when you give it that push? Is the planet super sensitive, or does it take a lot to get it to react?
And this is where things get really astonishing. After more than a century of research, from the very first estimates in 1896 all the way to today's massive IPCC reports, that range of uncertainty hasn't really shrunk. We're still looking at a likely range of 1.5 to 4.5 degrees of warming if we double CO2. That is a massive difference, and it's a core part of our mystery. So here's where we put the pieces together. We've got two huge question marks. How much are aerosols cooling us? And how sensitive is the planet really? So how on earth can two unknowns help us explain the one thing we actually know for sure, the warming we've already measured? Well, the answer is that they have to balance each other out. It's like a scale. To get the roughly 0.8 degrees of warming we've already seen, the two uncertainties have to work together. If the aerosol cooling effect is actually weak, meaning the total warming push is strong, then the climate must have low sensitivity. But if the aerosol cooling is really strong, shielding us from a lot of warming, then the climate must be highly sensitive to have warmed up this much already. Let's just lay it out here nice and simple. The warming we've seen so far could be explained by a world that's not very sensitive but is being pushed really hard by greenhouse gases. Or it could be explained equally well by a world that's very sensitive but is being protected by a strong cooling effect from our pollution. The problem is, just by looking at the past, we can't tell which of those two worlds we're living in.
And this leads us to what scientists have called a Faustian bargain. It's this incredibly difficult dilemma. Of course, we need to clean up air pollution. It saves lives, it stops acid rain. But the moment we do, we take away that cooling effect. We unmask the full warming potential of all the greenhouse gases that are going to be sticking around for centuries.
And this isn't just a turn of phrase, by the way. This quote captures the paradox perfectly. For decades, the very pollution that has been harming our health has also been, completely by accident, protecting us from an even greater amount of warming. We've basically been taking out a loan from the climate system, and the bill is coming due.
So this is the heart of the mystery, isn't it? And it's the challenge we're left with. That aerosol shield is temporary. It goes away as soon as we clean up the air. But the greenhouse gases are up there for the long haul. So as we do the right thing and scrub our air clean, we will, without a doubt, turn up the planet's thermostat. The real question for us becomes, how do we navigate a future where the solution we need might actually make the problem feel a whole lot worse before it ever gets better?